And we march on. This is lesson 27 in Math 222 at SUNY Geneseo. We are going to bound alternating series today. We are going to look at how good is good enough. And that's the basic plan. A little bit of vocabulary first. We should probably talk about a little bit of vocabulary, and I'm going to let that build off of our last discussion. This was the last slide in our last discussion. Think about the following for a moment. If we didn't have this alternation here, if it was just 1 over n squared, and 4n over n squared plus 4, would those series have converged on their own? Think about it. Right? So if these series were, we're going to go purple for a moment. If it was just 1 over n, that would have diverged, right? That's the harmonic series. But it's not the harmonic series. It's the alternating harmonic series. So the alternating series test kicks in and the thing converges. Whereas with this series, this one would have converged. It's a p series. P is bigger than 1. So whether or not it alternated is irrelevant. This thing was going to converge. So we actually have a way to talk about that. And the way we talk about that is we say if the sum of the absolute values of the terms converges, then the series itself converges absolutely. That is to say, it would have converged no matter what. If the series converges, but the absolute values diverge, then we say that the series itself converges conditionally. And the condition is the alternation. If it didn't alternate, it wouldn't converge. So this series converges, but it converges conditionally on the condition of the alternation. If the alternation weren't there, the series would diverge. This series converges absolutely because whether it alternates or it doesn't alternate, this series is going to converge. So what about that green one? Right, the green one converges conditionally because this behaves like the harmonic series does. This is basically 4 over n. So does it converge absolutely? Does it converge conditionally? Does it diverge? And so you don't know what I'm going for. I have 4 of them for you to consider. The sum of the negative 1 to the n plus 1 times 1 over radical n, the sum of negative 1 to the n plus 1 times 1 over n cubed, the sum of the negative 1 to the n plus 1 times n plus 1 over 3n plus 10, and the sum of the negative 1 to the n plus 1 times 3 to the n over n factorial. Okay? That's for you to think about. Do these converge? If they converge, is it absolute or conditional? Do they diverge? That's something to think about. So here's the other thing to think about. Consider the following. Bill Nye the Science Guy. I know. I know. So you take this series. It's a geometric series. You get 1/3 minus 1/9 plus 1/27 minus 1/81, and so on. You've got a geometric series. So the question is, if we approximate this series, with the sum of just 10 terms, how close are we to the actual retail price? How close are we? And remember how this thing goes. You go out a third, then back a ninth, then up a 27th, then down an 81st, and so on, and you settle down. The key to that whole deal was that if the terms don't get smaller, then the whole thing doesn't work. The terms have to get smaller. And so we have a general principle. I'm going to write it in purple because I like it. The difference between the absolute sum and the sum of n terms, that difference is always less than the first term you left out. It's always less than the first term you left out. So in this case, the error is less than the 11th term. We're going to add up 10. The error is less than the 11th term, which happens to be 1 over 3 to the 11th, and that's approximately 0.0000056450. And if you were to figure out the sum of this infinite geometric series and figure out the sum of 10 terms and subtract them, that error would be less than this number right here. And that's pretty close. That's pretty close. Now, I know what you're saying. Why would I try to approximate a series with 10 terms? Because this thing can be found. Well, how many terms are needed to approximate the sum of n goes from 1 to the infinity, negative 1 to the n plus 1 times 1 over n within 0.000001. How many terms are needed? Well, see, we don't know what this sum is. We just know that there is a sum. So since we know that there is a sum, we know that the difference between that sum and the sum of n terms is less than the first term we left out. Well, what's the first term that we left out? The first term that we leave out is 1 over n plus 1. And we want the error to be less than 0.000001. And it turns out that this means that, within, we want the error to be less than or equal to that. And so n has to be greater than or equal to 999,999. So we need 999,999 terms to get within this. So what happens in these kinds of problems? You have an nth term. You want to get a series within a certain value. We know that the difference between the sum and the sum of n terms is less than, strictly less than, the n plus 1th term. We want that n plus 1th term to be less than or equal to the error bound. And we do a little bit of algebra. And we're done. Okay? Okay. So for you to consider, how many terms will get us a sum within 0.000001. That's 1 over a million, incidentally. The sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 2/3 to the n. The sum as n goes from 1 to infinity of negative 1 to the n plus 1 times 1 over the ln of the ln of n plus 2. And that should do it. This, by the way, is an obscenely large number. This is not a very large number. Okay? Okay. Hey, thanks everybody.